All right, there we are. Basil. Hello, everyone, and thank you for coming. My name is Dave, and I'm here to talk about Bazel, the cloud-accelerated build system. First off, who is this guy? My name is Dave Stanky, and I've done a lot of things in my career. I've been a CTO for a small company in New York City. I've been a developer, front-end, back-end, mobile. I've been a sysadmin and an IT person. I've been a product manager, and I'm here today in my role as a DevOps advocate at Google Cloud. So we're going to talk about build systems today. And you've probably all used a build system, though you might not think about it very much. A build system is the thing that takes our code, as well as maybe some metadata, test definitions, that sort of thing, and runs it through a bunch of processes, like linting or static analysis, compilation, transpilation, linking, and then importantly, testing, and it spits out some stuff at the end. You can think of it as kind of a function, takes inputs, does stuff, gives you an output. And that output includes both binaries, artifacts, things that you want, as well as test results that tell you, was this code good or not? And I do want to call double attention to the word test here. We call these things build systems, but we really should call them build and test systems. The testing is typically the more crucial part of it, really. The building is relatively easy. Everything I talk about in this talk applies equally to build and test. And sometimes we may use the word build, but we mean build and test. And sometimes I'll use the word test, but I mean build and test. So do we have any Java developers here? Probably, right? So I bet you've used things like Maven or Gradle. If you've ever played with C, you might have used something like make or CMake, which is a wrapper around make. In JavaScript world, you've got Webpack, Gulp. If you're doing Go, has its own embedded build system called Go Build. So there's all sorts of build systems. And the key takeaway that I want you to have today is that you have a choice. And the one I want to talk about is called Bazel. Bazel is Google's build system, available as open source software, and a great choice for building and testing your Java applications or any language application. Using Bazel as your build system of choice, you can build and test your code faster. And Bazel has the ability to leverage the cloud for even faster build and test of code bases at scale. And I'm going to show you that in a demo later on. So what are we building and testing? We are building and testing increasingly big code. Big code. Code bases are not getting any smaller, right? It's typical a day at your job as a software developer is writing a bunch of code. Every once in a while, you might delete some code, and at Google we have a good culture of praising people who do so, but it's only brought up because it's so rare. Code bases just get bigger and bigger and bigger, whether that's first-party code, third-party dependencies, metadata, etc. How big? Well, here's Kubernetes, popular open source package you've probably heard of. It's got about 1.5 million lines of code. Here's Linux, which is on the order of 20 to 30 million lines of code. Here's Windows, which is, of course, proprietary, but it's believed to have about 50 million lines of code. And here's Google. Oh, oops. Let's zoom out a little bit there. There. No. Almost. Here's Google's code base, which we keep in one giant mono repo, and it contains 2 billion lines of code. 2 billion. Last time, I promise. So we build and test 2 billion lines of code multiple times every day. Our entire code base is kept live, active, up to date, and it's all considered as part of one giant build. And doing so requires a special kind of build system. Before that, I just want to talk briefly about how that code is stored. There are a few different choices here. We've got a mono repo, means one big repo, and that's what we do at Google. A lot of big companies do that as well. And increasingly, that's something that's becoming viable in the Git world. We all know that Git has some scaling limits, but talked to a very smart person recently who said that he expected that it would be solved by the end of 2019. So keep throwing your stuff at Git, someone will figure it out. But you can also do the same thing with a bunch of repos, whether that's 5 or 10 or 20, or people have told me that they have tens of thousands, I've heard from customers. And then there's this new concept I've been hearing about called a meta repo, which is stitching together multiple repos into one big representation of all your code and addressing multiple repos as if a single repo. Regardless of how you store it, you have a ton of code and you need to operate against it. Operating against it means you have a big build, and big build means big tests, right? Because we're testing all of our code all the time, really thoroughly, making sure that it's really correct and gives us the results we want. But let's talk about testing. So testing is great, right? There's a lot of research out there that'll show how thorough attention to testing leads to better code quality, more uptime, more end user satisfaction. You make your users happy, and then you make your managers happy, and then they give you raises, and that makes you happy. It's all awesome. And when we add test automation, which is typically what we're talking about when we talk about CI systems, we're going to get better speed and more reliability. We're going to be able to deploy more frequently and more confidently. It's great. Look, this isn't a red-green pro-con, right? This is just all green. Testing's amazing. We've all bought in and we're all doing it. Or not. So we did a study with a whole bunch of organizations of all different sizes. This was across hundreds of companies. What we found is that fewer than 30% of teams are building every code change that they do. So a lot of things are hitting their repos without testing. And even fewer have comprehensive coverage. By comprehensive, I mean that every code path is exercised so they are confident that every bit of their code is correct. So why aren't we testing? If we're so confident that testing is good for our organization, and we've all bought into it, and we all go to conferences and we tell everyone about our test automation systems, why aren't we doing it? Is it because we really like getting woken up by that 3 a.m. page? I don't. It's because testing takes resources. It's very common that you set up you write your code and you kick off a test, and then you watch your ticker, and what do? Right? You go to lunch. Okay, you come back. You expected your test was going to be done. No, not done. All right, so now I'm going to go get some coffee, check Facebook. Come back again, it's still churning, 84%. All right, let's go get a beer, and then come back again. All right, it's the end of the day. Maybe it'll be done tomorrow. Eventually, though, we got to get back to work. So what do? We take shortcuts, right? We start turning off pieces of our test suite, committing something that I think it's going to work. I'm pretty confident about this. I'm not going to worry about it. The nightlies will pick it up if it's a problem. And let's talk about nightlies. Why do we even have nightlies? Because our tests are too intense to run all the time. So we would like to run our tests all the time, but we're constrained. This leads to what I call the testing conundrum. The more we test, the better our code gets, the more rapidly we can deploy, let's say. And that leads to fewer software defects, right? That's what we want. But our overhead goes up. We need more machines. We need more time. So what's the sweet spot in here? You really can't pick what is appropriate level of testing versus defects. You can either ship it now or you can ship it right. And I know I've never had a manager who really is going to let me make that choice. It's yes and yes. But what if we could change this dynamic? What if we could flatten the curve? If we can have a system that lets us run all of our tests without linear scaling of the time and resources, then we can scale our software, scale the complexity and size of our code base without losing the velocity. If only there was a build system that could do something like, oh, look at that. So Bazel is Google's build system, and it's open source and has been for a few years now. It's been used at Google for over 10 years. Bazel is a modern system built from the ground up to scale and have correct, reproducible builds for any size code base without losing any velocity. At Google, we built Bazel because we had to. We had a ton of engineers writing a ton of code. No, I'm not going to say it again. Remember, it's a lot of code. 30 million commits. What's the number? 30,000 change, or 60,000 actually is the number, running every day. There's some great stats. You can find them online. 60,000 changes hitting the code base every day. And this is one giant mono repo where we're testing across the impact of the changes across that entire mono repo 60,000 times a day. You simply can't do that when you're running with something like Make, which is where we started, and it became unwieldy. So we created Bazel. Today it's in use by nearly every one of Google's 40,000 something engineers to build everything from search to Gmail to Photos to Google Plus to your favorite app Maps, as well as Android and iOS. And we have features that allow it to use the power of the cloud. Inside Google, engineers use a huge fleet of distributed workers, and that's something that's now available in the open source version as well. So Bazel is built on two core optimizations. The first is don't repeat yourself. If you've run a build, built an artifact or run a test before, why build it again? And Bazel's model allows us to reuse prior results with complete confidence. And secondly, for things that you do need to build, let's use parallelism to fan those out and execute them across a large number of workers. So in order to understand Bazel's optimizations, let's take a look at a traditional build system. So here we have a portion of the TensorFlow code base. It's actually a small portion. TensorFlow's got a lot of code in it. And we're going to build it, and we're going to come up with something that we can actually run, in this case, a library. So with a traditional build system, our approach is something like this. We're going to grab all this stuff, and then we're going to do this thing and that thing and the other thing, and then we're going to cross our fingers, and hopefully we get something out that we can use and give to our customers. Now, there are two problems with what I just said. One is all the things. Do you really need all that stuff? Maybe not. The other is this thing, then that thing, then the other thing. This all sounds rather serial, and of course, this is the age of parallelism. So with Bazel, we take a different approach. We start by observing that this is not arbitrary stuff. This is source code. Okay, mine sometimes is a little arbitrary, but yours, hopefully, is a highly structured system of interdependent symbols. And so using Bazel's build system, build language, we declare what the pieces of our code mean so that Bazel can understand them and reason about them appropriately. Then Bazel interprets those and feeds the inputs into the action, putting out the output. So each one of these individual bits gets composited into what we call an action. An action is an atomic unit of compilation or testing that says inputs to outputs. You can think of it like a functional transform. And each one of those actions has a unique signature, which means it's independent from each other. All of the inputs are completely declared, the outputs are completely declared. Therefore, you can observe them and operate them on independently. We then compose these up into what we call the build graph. That shows the sequence of dependencies, what needs to be built before everything else to get from our initial source all the way to our output, our artifact, and our test results. And here's our first optimization. We can cache the inputs of each of these things as a hash. If the inputs don't change, we know that the output is going to be the same. Therefore, we can reuse the output of an individual action and skip all the work of actually doing it. Now, if the inputs do change, then we need to do some work. So let's zoom out on our build graph. Let's say this is our application that we've built, took our inputs, ran them through all its steps, came up with an output. Now let's make a change. So let's say our change impacted this bit and this bit here. These are, say, files or test suites, whatever they are, the inputs to our build. So we are going to have to do some work. Walking in the graph, we can see that all of these bits are going to be invalidated and need to be recomputed. So that's a lot of work we got to do. But importantly, all the other bits are untouched, and we know with absolute certainty that we don't have to rebuild them. The other thing we can observe is that this chunk here and this chunk here don't share any edges. Therefore, they can be executed independently in parallel. So putting it all together, it looks something like this. I say, Basil, test my work. Basil's going to grab all my inputs and compose that build graph. Then it's going to consult its cache to see which bits have already been done and trim those, prune those out of the build graph. No need to rebuild those. Then fan out across all the cores on my machine to create my output. What can you build with Basil? Everything. Here is a small sub-list of all of the things that have that you can build with Basil. Basil includes an extensibility mechanism. It's a language we call Starlark. It's a lot like Python, and it lets you build plugins, or what we call rules, language rules. And what that means is these are the rules for how you build this language or that language. And the community, the Basil community, has contributed dozens of languages. And if there's something that you would like to build and you don't see it here, you can use the Starlark language. It's pretty easy to pick up, looks just like Python. It's actually a stripped subset of Python, but it's not Turing complete, so that you can't create infinite loops. And you can build out your favorite language. I like to show this list to people at conferences and say, well, what are we missing? Is there something you want? And I had someone recently come up and say, well, okay, smart guy, what about OCaml? And I was like, what the heck is OCaml? So I went and Googled it on my phone, and it turns out, yeah, we've got OCaml rules. There's really a ton more that you don't even see here, and over time we expect there to be all of them. All right, so demo time, and I'm more nervous than usual. I'm always a little nervous, but let's take a look at building something with Basil. So, let's see, we're going to start. And look, I lost my connection to my machines. Fingers crossed I can get it back. I apologize for the small type, but these are chatty programs that need to spit out a lot of stuff. Okay, good. We are coming back. On the left, what we have is a machine that's going to run Maven. And on the right, we have a machine that's going to run Basil. These are identical machines running in Google Cloud, but they're just Ubuntu 16 machines. So let's go to my application. And, oops, demo app. All right, let's take a look at this application. So what I'm going to show you is a small, lightweight Java application that wraps the TensorFlow library. And TensorFlow is written in C++. You're probably aware TensorFlow is a machine learning library developed by Google and available as open source. So we can just take a quick look at what this application does. What we're going to do is image recognition. So there we are. The first thing it's going to do is say, which image do you want to do? I have it preloaded with some standard stock images. We can take a look at one. And it's going to render here in ASCII. It actually runs really quick, but I think the Wi-Fi is saturated. Yeah, it's trying to bring ASCII back over the wire, which you really would think would be fast. I don't know that I have it gzipped. Try it over here. Maybe this machine will run faster. Yeah. All right. So we're going to get an ASCII representation of an image, and we can see with our personal human eyes what it looks like, if it ever shows up. And if not, you might just have to take my word for all of this. Tell you what, let's take a quick opportunity to show you github.com, Bazel build. So this is the Bazel organization on GitHub, and in here you can see all of the different rule sets. And this is not even all of them. Some of them are hosted by independent folks. Sass, Node.js. There's also rule sets for like creating iOS and Android outputs, in addition to the language bits for creating those. All right, here we go. So, anyone want to guess what that is? I think it's sunglasses. Let's see if TensorFlow agrees. And TensorFlow is thinking hard. Sunglass. All right. 61% confidence by TensorFlow. I won't show you the other one because this is running a little slow, but you can still choose to play guess the image. What's that? Yes! And TensorFlow agrees as it happens. All right. So now let's make a change. I'm going to have to quit out of there. Come on. Is this thing bricked? All right, you know what? Let's try doing both of them on the machine on the right. So I'm going to make a change to my Java code. Oops. And again, remember that the Java code wraps TensorFlow, includes it as a native library. Source main. Oh, good. This one's, at least it quit. Source main Java. And then it's all of this stuff, and we have a greeter class. And we'll go ahead and make that change on both sides. CD. All right. I am trying to open a very heavyweight IDE called Vim here. All right. In the interest of time, maybe I will describe what would happen here, which is that we run Maven, and it runs everything single-threaded, perfectly fast, but not as fast as Bazel, which runs everything multi-threaded across 16 cores on this machine. Do you think I should try the other Wi-Fi? They gave you a special speaker Wi-Fi, making us believe that it would be super fast. Now I've probably lost my connection, right? Oh, that seems faster. All right, so we're going to change our greeting from hello world to hello, oops, hello Ukraine. Did I spell that right? Yes. And what's the deal? Is this one connected? Probably not. We'll do this asynchronously. Usually I do this in parallel. And then we're going to retest. And this will be something that looks super familiar of a Maven test running through. And then on the right side, we will make the same change. Oof, this is slow. Oof. And so we're running through all of our test classes. It's running. And at the end it should be just about done there. What I'm trying to do here is help you understand the experience of waiting for your tests to complete, which I'm sure is something you've never experienced in real life. This is what it feels like to be a developer. And this is that point where we go out and we get a beer, and then we go to bed. I really want to show you the Basil part. But you know what? Back to the strawberry. Let's go ahead and we will skip to the ultimate payoff, which is coming up soon. All right. So what I just showed you is that we made a change. Basil consulted its cache and only rebuilt or retested the things that had changed, fanned out, and used all the cores available on my machine for its build and test. So, who's using Basil? Well, a lot of really cool companies and organizations are using Basil, including Wix.com. And I want to point out Natan. Stand up, yes. Natan is giving a talk after lunch right across the hall in space C, where he's going to talk about migrating to Basil at Wix. Challenges, successes, and he'll also be available to take questions about his experience migrating to Basil. There's also a lot of folks that aren't necessarily represented here. Basil is very popular with self-driving cars and with aerospace. It's funny, today's keynote was in a place called SpaceX. SpaceX is actually a Basil user, you know, with the rockets and shooting Elon Musk's car into space. There's a great talk from BasilCon that you can see of them talking about using Basil for embedded systems. So the demo I showed you was using 16 core machines. Now, I don't know about you, but I don't use a 16 core machine. I use this cruddy little 2-core machine. But even if you wanted to, you could go out and get 16 core machines for all of your engineers. And most of the time, they'd be really happy because Eclipse notwithstanding, an IDE doesn't really take that much power. So they're typing away, happily writing code. Their machines are completely underutilized. And then they run a build, and maybe it's something not too crazy, and they're still pretty happy. It's not really stressing their machine. But at some point, when we have big code, they're going to end up flooding their machine. And that machine that was underutilized now becomes overutilized. And yes, even with Basil, you can max out the entire capacity of one machine. But it's not like we can conjure up new cores out of thin air. Or can we? So remember that each of these items is an independent action, fully specified inputs and known outputs. Therefore, they can be distributed to all of the individual cores on your machine or to cores that are distributed across a network. So just how it worked when you're building locally, we used all 4 cores, let's say. We can go further with the cloud and use a ton of cores. We also can take advantage of a shared cache, which means everyone in your organization can get the same cache results. If I built it and you're setting down to run the same code, you don't need to rebuild it. Grab my results out of the cache. So this is great for general velocity, as well as really good for onboarding new users, where you don't have to, quote, build the world. You just pull it from the cache and off you go. So this is Basil Remote Execution. It's based on an open source API, which has been contributed to by Google, by Uber, folks at Bloomberg, and you can find that in our repo. And using the remote execution service allows us to create a build system that can work against a hosted service, whether that's on the cloud or on-prem. The worker pool can scale up and down according to your needs, and you get that shared cache. There are multiple clients for this API, including Pants, that's Twitter's build system, BuildStream, which is being built by folks from ThoughtWorks and Bloomberg, and of course, Basil. So that's on the client side, clients that can consume this API. On the server side, these are the implementations that I'm aware of. There are several open source ones you can find in these places I said. And then at Google, we have a hosted version where it's fully maintained a service that we provide as part of Google Cloud. It's in alpha, and if you're interested in checking it out to accelerate your Basil builds, you can send an email to RBE Inquiries. I'm on the list that receives that, by the way, so if you have questions related to this talk, feel free to do so. And we'll hook you up with folks who can help you get onboarded to try out the alpha service. We're, of course, hoping to bring that into GA soon. So let's see how we can do with the demo. I'm not sure what we're going to be able to achieve exactly, But I want to show you what we're going to do. We're not going to do the race because I don't want to use any more compute, or not compute, the compute's not constrained, any more network than I have to. I'm going to hop onto a machine that's same style of machine, and this time we're going to build the TensorFlow core. And, you know, because we're only going to use one. Usually I do this side by side, and everyone takes bets, and oof again. All right, let's try this one last time. Let's switch back to the other secret Wi-Fi that's just for speakers. Maybe that one has cleared up by now. I mean, there's really almost no traffic happening. It's just the terminal. All the compute's happening in the cloud, but it is happening in the U.S. as it happens. So maybe that's what I get for trying to go transatlantic with this. In my hotel room, I swear it worked like a breeze. All right, so now we're on a machine. We're going to run Bazel. So we're going to go to the TensorFlow core, and I'm going to make a small change. I'm going to go to file strings numbers.h, and I do really not know C++. So if you happen to know C++, I'm sorry for whatever I'm doing here. And oh, okay, we can do it. We can do it. I'm just pushing arrow down. That's it, just down. Just trying to get down to a little bit further down in the file. Almost there. We're going to scroll now. Get ready. I'm not going to touch it for a second. It's going to scroll. This is honest-to-God TensorFlow code. I didn't write this stuff, which is why it's probably pretty good. You can see that it's the Apache license, which is a very permissive license. Encourage to try it and use it in your... Here we go. Okay, so I've got this. This is just a string. Should have known that would happen. Back up to there. A bunch of utility stuff in here that are used by the TensorFlow library. I can take this moment to give a little pitch for the Google Cloud has a bunch of really cool API, machine learning APIs that you can use without having to actually know what all this stuff does. There's some really neat stuff to automatically train your models and automatically use the models. Okay. This is, anyone ever use a modem growing up? Does this feel familiar? 14.4 kilobaud, perhaps? I'm going to go back to my slides, and you are going to take my word for it. So, well, that doesn't make any sense. There we go. So what I just showed you was using Bazel with a shared cache to not redo, to eliminate rework, a scalable worker pool to distribute new work across 600 workers. It's a lot. And this is actually one of my favorite features. I hopefully can get you a screenshot at least. Oops. A structured result UI. So what happens is Bazel will emit this structured data about all of the builds that it did, the individual targets and the pieces of work that it failed and succeeded at, and then it'll bubble up the failures right to the top of this web UI. You can share that with your coworkers and say, hey, here's a failure, what does it mean? And your coworker can say, oh, I wrote that code, I know how to fix it. It's a lot better than reading a big standard out file. Now, when you're running Bazel and CI/CD, there's a couple cool things you can do. So, of course, Bazel, or any CI system that you might be using, can power, any CI system can power Bazel, and it's going to run its magic. And that cloud cache and that cloud compute can be shared through your CI workers just the same way as it's shared through your individual workers, your developers. And what that means is that the work that your CI system does is incremental to the work that your developers did and vice versa. Everyone can reuse that same cache. And because of Bazel's correctness promise, you have confidence that the work that's happening is correct, and there's going to be no flaws introduced accidentally. So it's very typical in a CI/CD pipeline to do what's called a clean room build. Right, even if you're using incrementality on your developer machines, typically your CI system is going to rebuild the world. But with Bazel, that's actually not necessary, and your CI system gets that same incrementality. So no more of those full, heavy builds. Everything is fast, and you can rebuild every single change without having it be a nightly build. So a lot of folks are starting to take advantage of remote execution with Bazel. Here's just a couple examples. This is Android Studio, who's using it to build their IDE, running headless builds, a full headless IDE in a remote worker and for their testing. And they've seen a 4x improvement in their overall experience. TensorFlow themselves are using this. And if you submit a pull request on TensorFlow, it's going to be tested through machines that are running against remote build on Bazel. And they've gotten a 5x improvement. And additionally, they've seen a 5x reduction in the amount of hardware they need to use. So that's a double 5x, which is pretty cool. There's also a number of companies, proprietary, that I'm not able to disclose, who are using RBE as of today in its alpha state to accelerate their builds. I can say that Wix is there because he's going to talk about it later today. As well as there's several companies using the open source versions of these tools for their builds. So these are things that Google wants. I kind of think they're things that everyone wants. You want faster builds. Your testing to be really comprehensive, no shortcuts. You want to save your developers time so they can focus on doing important things that use their brain. You want to deploy frequently with the confidence that your deployment is correct, that you fully tested it. Then that's no matter how big the code is. So with Bazel, regardless of how big your code base is, regardless of what languages you're using, if you have a polyglot application in one repo or multiple, you can cache across your invocations, you can use every core in the cloud, and have a shared infrastructure across your users. So if you're ready to get started with Bazel, visit bazel.build. Yes, .build is the TLD. We're into that new TLD thing. If you want to get started with remote execution, you can find these open source implementations on their respective repos, or if you're interested in using our hosted one from Google, you can email that address to get information. And with that, I will be happy to take questions. Are there any questions? If not, I'm going to make you watch me try and make this darn thing work, because it's so cool, I swear. Just imagine you're seeing something super fast and cool and precise. Yeah, this is, I can't imagine how bad this is. Like really, this is sending 50 bytes across the network and trying to get 10 bytes back. But I'm not here to complain about the Wi-Fi. I know how hard it is to make conferences. Are there questions? Yes. Oh, actually, ask it with the microphone because I can't even quite hear you.
Could you tell how Bazel split your actual code to the actions? So how it determined that this part of code is like atomic and so on?
So Bazel uses build definitions. You write them in what's called a build file. Those can be hand edited, or depending on the language, there may be auto generators for them that says what pieces rely on which. So you'll have a section that says this is a Bazel, this is a Java library that depends on this other library that depends on this other library. And then within that, we call it a target. Within that, the source files are monitored for changes.
So basically, we define the relationship in the code.
You define it, and or you use tools that can interpret from your code. So something like Go, which is highly structured, it's really easy to interpret the code and write a build file definition. With Java, there are a couple of tools that are out there in the ecosystem that can interpret your code, look for the dependencies, and write your build file definitions for you. Okay. And I think Natan will be talking probably about how they did that. Am I right? Now you have to. Other questions? Roman, who I know knows a ton about Basil.
But I'm just actually curious that like one of the things that we're seeing is you were building on remote server. And so obviously you had an amazing network connection between your remote server and the cloud. Now, in case if you would have a much worse network connection, how much this cloud build is intensive in requirement of your networking. It's amazing that it can take all the resources on the cloud, but how much channel it needs to do this?
First of all, I love how you said, I built it on the cloud, keeping up the fiction that we actually saw in my demo. It's a great question. The question is, doesn't this mean a lot of chatter back and forth between the place that's running Bazel and the cloud? The answer is yes. It's a very talkative protocol and has to send all your source files up, get results, and get them back. If you have a fast network connection, awesome. If you don't, one of the options that you can do is actually what I tried to do. And I mean, this one's absurd, right? I was just trying to SSH to a machine. But you can have your Bazel workers actually be in the cloud, whether that's just as machines. I know people who give their engineers each a VM in the cloud and say, that's your workstation, and then that connects at line speed against cloud resources. Or you can use like a CI system and you can run that in a one-off and say, I'm going to do an incremental build with my CI system, again, where the worker is in the cloud talking to the farm in the cloud. And finally, there is some fallback. It's actually under development so that if your connection is bad, it'll run locally. That's new, but we're trying to really emphasize that for the, the airplane use case or whatever. Questions? All right. Well, then I guess we'll head to lunch early. Not even that early. And one more time, I encourage you to visit Natan's talk to ask him the hard questions about how you actually do this in practice and how to make it work with engineers who might say, I don't like this tool, I've never heard of it. I believe it's worth it. We'll see at his talk if Wix found it worth it. Thank you.